Okay, so this is the extra problem solving session for the exam, September 13th. And the forum I opened for this has no requests in it, but I did happen to check the one from like Monday, and I saw some requests there, so I'm going to do those two problems. That's not where we should be. Okay, so the two requests were for from the review problems 14 and 15. So So for problem 14, this is like the one from our most recent homework, where we're trying to find curvature. At a point. And because we're given the function in that form, this is one of those ones where it's easier to use that formula that I put up on the board, I think last Thursday in class. So we're going to want to use the formula that curvature kappa is equal to the absolute value of f double prime divided by 1 plus f prime. Actually, I should do the notation with the x. That way it's easier to see the squared. So f double prime of x, and then that denominator is to the power of 3 halves. So in this case, y is that f of x, and for the WebWork example I opened up, that function is 2x plus 3 over x. So all you have to do is plug it into the formula, that function for f, so you're going to need to take two derivatives. And then just plug it in. Oh, this is a little too far over. There we go. Then it asks you to evaluate it at x equals 3. So you go ahead and do that. This problem is one of the types that you need like the least amount of new knowledge to do. The derivatives are of a single variable non-vector function, so you just take those derivatives like you normally do and then plug it into that formula. So it can look intimidating, but it's really not. And you the only problem you might have is if you try to use that R vector version of curvature, you'll get the right answer, but you do have to convert the function y, a function of x, into a vector valued function first, and then take those derivatives. So this is one of those ones where overthinking it can make it harder, but by itself it's not really that difficult. So just be careful. Don't make more work for yourself than you have to. And then the other request was for problem 15. So let's do review number 15. Find the x-coordinate of the point of maximum curvature on the curve y equal 3 e to the 4x. So this is the one that I think we actually did this in the problem solving review session on Monday too. So it's just combining curvature with ideas about optimization that you might remember from like Calc 1. So there are two parts here. So the first is even ignoring this like weird request that they want you to find the x-coordinate of the point of maximum, we see curvature. So we know that we're going to have to do a curvature problem. So even if you can't figure out the rest, just like a strategy for this kind of thing would be go ahead and do the thing that you know you can do. curvature is a word we learned in this section, and we have a nice formula to apply it, so go ahead and do that. And again, because we're given y a function of x, it's going to be easiest to just do that f double prime divided by that 1 plus f prime to the 3/2, where f of x comes from our y, so it's that 3e to the 4x. And then you would just take your derivatives to plug in. So this part is going to go here, and this part is going to go here, and then you're just going to have kappa is going to be a whole mess of stuff over stuff. But the important thing is that it's going to depend on x. I've got this e to 4x that appears in both my derivatives, so when I plug those derivatives into the kappa formula, I'm going to have x's hanging around. So unlike the problem we just talked about where they give you an x value to plug in, this one doesn't give us a specific x value to plug in, so those x's are going to be important for the second part. Which is to maximize kappa as a function of x. So they say find the x coordinate, so you're doing something with x's, of the point of maximum curvature, and you want to find the maximum curvature. So this is about taking that kappa that we know how to calculate and just finding a way to make it as big as possible. Whenever you learned how to maximize things back in Calc 1, it would have been to, oh, I just noticed there's a participant in the Zoom. I hadn't turned on screen share because nobody was here. Let me do that now. Hi, Micah. I'm working on the problems that I think you requested. Let me see if I can get the chat open too. I don't know if you've been here long, Micah. Do you want me to go back and start over?
No, I just joined.
Okay.
But, yeah, it was just problem 15. I figured out 14.
Okay, cool. Well then, I'm recording this. Are you okay that people will hear you?
Yeah, that's fine.
Okay, cool. So I'll just go back to the start of the notes on this page, just because you're here. So kind of, problem 15 is just combining the idea of curvature from problem 14, which you already figured out. But what's going to happen is because they don't give you like a specific value x to plug in, the curvature you get from the formula is going to depend on x. So like you're going to plug in this e to the 4x in your f double prime and f prime, so there's going to be x's on top and bottom. And so then when they ask you to find the point of maximum curvature, they're asking you to maximize something with respect to x. Oops. And so from Calc 1, hopefully you remember that maximization just means set derivatives equal to 0. And check that it passes the second derivative test, usually, but in this case it's set up so that there's just one point and it's the maximum. And when I say derivatives, I mean kappa prime of x is going to be equal to 0. And that's going to give you the x0 that you need. So there are no other requests, so I can go ahead and show this in more detail if you want to see it, or if you feel like you've kind of got enough to go off of, I can stop here.
Yeah, could you actually like work it out?
Yeah, sure. Let me actually steal this part, that way I don't have to redo it. Oh, where's my copy button? That must be it. Okay. So as far as the curvature part goes, we've got this formula for curvature, and I went ahead and took these derivatives. So I'm going to get that on top, it would be 48 e to the 4x and on bottom it would be 1 plus 12e to the 4x to the 3 halves. Exponentials are always positive, so I don't need to worry about these absolute values anymore. I'm just going to move this a little bit out of my way real quick. So this is going to be 48 e to the 4x over 1 plus 12 e to the 4x to the 3 halves. And eventually I want to have the derivative of kappa with respect to x is 0. So first thing I have to do is take that derivative. So I'm going to swap my 3 halves in the denominator to look like a product of two things where one has a negative exponent, just so that I don't have to fool with the quotient rule. So I'm going to go ahead and do a product rule of kind of this is my f and this is my g. So that's my f prime. That's my g. That's my
For
f.
the curvature formula, I thought the f prime gets squared.
Oh shoot, it does. It totally does. Did I copy that? Yep, I just copied it down wrong when I moved over to the next slide. Thanks for that. So then this is actually going to be, I'm going to call it 12 squared e to the 8x. Instead of multiplying out that 12. Like that. Does everything else look okay up to here?
Yeah.
Okay. So then my g prime is going to be negative 3 halves 1 plus 12 squared e to the 8x to the negative 5 halves. That's minus 3 halves minus 2 halves is minus 5 halves times the derivative of what's inside, so that's going to be another 12 squared times 8 e to the 8x all together. And that's my g prime. And I'm going to want to set this equal to 0, but it's a little bit easier if I do some simplification first, so I'm going to try to pull out some like terms. I've got this common e to the 4x. 48 was 4 times 12. But I see a 48 in both, so it's fine. And then I'm going to go ahead and change this 8 to a 4 times 2. That way I can also pull out a common 4. So I'm thinking about this term, and that all coming out front. As well as the g part. So then the f prime g, I've pulled out all of that, and then all that's going to be left over is going to be this negative 3 halves times 1 plus 12 squared e to the 8x to the negative 2 halves, so just negative 1. And then that 12 squared, and then that 2 left over from when I split that 8 into 4 times 2, e to the 8x. Like that. Do you have any questions there, or does anything look odd?
No, I'm good.
Okay, cool. So we're setting that equal to 0, which means that really we just care about the thing inside the brackets being equal to 0, because that part will never make it 0, because exponentials never become 0. So what we want to find is 0 is equal to 1 plus, well, we'll switch it to a minus now. 1 minus 3 halves, 1 plus 12 squared e to the 8x to the minus 1, 12 squared times 2e to the 8x. And I'm going to go ahead and copy paste that over to the next slide if I can. So we've got that. And then it's just an algebra problem from here of trying to set this equal to 0. So I'm going to go ahead and say I've got 3 halves, 1 plus 12 squared e to the 8x to the negative 1, 12 squared times 2 e to the 8x is equal to 1. Just moving the negative over to the other side. And then I'll go ahead and multiply by that 1 plus 12 squared e to the 8x. On both sides to get rid of that negative exponent. These 2's cancel out, so I'm looking at 3 times 12 squared e to the 8x is equal to 1 plus 12 squared e to the 8x. Or subtracting the 12 squared on the right into the one on the left, it would be like 3 minus 1, 12 squared e to the 8x is equal to 1. Or just 2 times 12 squared e to the 8x. So I've got e to the 8x is equal to 1 over 2 times 12 squared, or 8x is equal to natural log of 1 over 2 times 12 squared, or x is 1/8. Oops. 1/8 natural log of 1 over 2 times 12 squared. And that's going to be my x0, because I set the derivative equal to 0, so it's going to be a maximum or a minimum, and it's the only solution to that, so it ends up being a maximum. And that would be what you put in this first spot. And then after it asks you to find the maximum curvature, that just means go back to your curvature formula and plug in x0. And by that I mean this formula right here. But everywhere you see x, you'll switch it to this value right here. Which becomes kind of messy. You can, at least for the e to the 8x, use that it should be that value. But the numerator might look a little weird. Do you have any questions about that?
No.
Okay. Cool. Well, that's how you finish the problem. So I'm not going to do this part because I don't have a calculator with me. And you don't have to simplify it in WebWork either. You can just kind of plug the whole mess in.
Gotcha.